Hi there, my name is Nigel Bayliss. I'm the Optimizer PM. I'm going to talk to you today about SQL Plan Management and specifically the latest enhancements we've made in Oracle Database 19c onwards. The driver for the changes we made were in fact for the Oracle Autonomous Database, so I'm going to be covering that first. But the good news is a lot of these changes can be used if, for example, you're upgrading from an earlier release to 19c. So you'll find some of the features that we've included are going to be useful in those circumstances too, for, say, an on-premises database as well. So quick introduction. So you'll know Oracle SQL Plan Management has been around for a long time, since 11G. The idea behind it is to control SQL execution plans. So in other words, only SQL statements use only approved SQL execution plans, and they're held in the form of SQL Plan baselines in the database. They're typically, you can split the use case really into two parts. In fact, the primary use case for SPM was originally the strategic and preventative approaches. So the idea behind it is that you can control all SQL execution plans for your application proactively. So in other words, the idea behind it is to be a preventative measure where your application has a particular set of SQL, you control that SQL and ensure that execution plans never regress in terms of performance. Perhaps slightly more common to that is a lot of customers use it for critical application workloads, so you'll use it in the sort of core of your application. But overall, I guess what grew to prominence and is used more often these days is more of a tactical and reactive approach. So in other words, you have a SQL statement that's worked fine for a long time, then you use SQL Plan Management to control the execution plan when it's proved to be problematic. So typically, a SQL statement may experience a performance regression, and then a SQL Plan baseline is created to control that execution plan to prevent that from happening again in future. So if we look at the strategic or the preventative approach, the way you do this is you can specify which SQL statements you want to capture. So for a particular application, you initiate the capture by setting a database parameter. Those plans that are seen are encoded into SQL Plan baselines, and you'll be able to see those gather and get created in the SQL Plan baseline views. Ultimately, when you're done, you turn the capture process off. And then from then on, the SQL Plan baselines are going to prevent the plans from changing without prior approval. And approval can be a manual approval, or it can be an automated approval using the process of Evolve, which test executes different plans and figures out which ones should be accepted and available for use. A tactical approach is different, of course, as you'd expect. So here, the users, for example, may notice a performance problem that gets reported or sometimes noticed via EM Cloud Control, perhaps. And then there's a manual. This is where the manual approach will kick in. So you'll identify performance regression using AWR, using different tools like Enterprise Cloud Control. You might use SQL Tuning Advisor to figure out whether a SQL profile will fix it. Generally, a number of different steps that can happen, and then that often will result in a SQL Plan baseline or SQL profile being created to control that execution plan into the future. So what are the goals of automation in this case? Well, the goal is to automate a tactical approach. So in other words, we create SQL Plan baselines for SQL statements that have or are experiencing a SQL performance regression. So it's a tactical approach, see the regression, repair it, and then move on. So the idea is that without any manual intervention, we spot the SQL performance regression first of all. The database identifies it automatically. Then the database can, in fact, locate previous SQL execution plans, test execute them offline in the background, and figure out which are the best SQL execution plans to use. And then the result of that will be to create a SQL Plan baseline to enforce the optimal plan or the best plan that it can find. So what's the user experience look like with automation? So in an autonomous database, you might have a SQL statement that's been running for a long time without any issues. Then suddenly the performance declines significantly. Offline and automatically in the background, SQL Plan Management identifies that a performance regression has occurred, and then it will reinstate a previous SQL execution plan if one exists and is proven to be performing better than the current SQL execution plan. So it's a different color on this slide because it's not necessarily kind of an obvious part of the user experience. We have essentially the next step is the SQL statement then works well again. So the user experience is it occurs, it then gets repaired, and there was no manual intervention. So that's the key experience, if you like. So let's take a look at the implementation and a quick step back or step to one side. There is a new infrastructure component called the Automatic SQL Tuning Set. We exposed it in 19.7, and it was on by default briefly. It's off by default in Oracle database RU 19.8 onwards. It's pretty straightforward to understand, in fact, that what we've added is a system-owned, system-maintained SQL tuning set. So it's not something that, again, requires manual intervention, but it collects application SQL in the background. It was originally conceived, in fact, to support automatic indexing because the automatic indexing feature needs to collect application SQL and test execute it against new candidate indexes to figure out whether the performance is improved or not. So this is a new component. It is available in Enterprise Edition, so you can use this in on-premises as well. In Autonomous, it's something that just happens in the background, so it's always sitting there operating. It is a very useful resource because, in fact, what's actually in there is a history of your application SQL statements over time and the different execution plans that we've seen. So we have a history essentially going back for over a year, which tells us what SQL was executed and what SQL execution plans we used. So let's look at this little background task, the thing that's going on. If we break it down a little bit more, we can identify resource-consuming SQL statements in AWR, which is something you're probably familiar with. So we get the database to do that for us. So it can introspect AWR. In fact, it can introspect the SQL tuning set as well. We then can locate alternative SQL execution plans in the automatic SQL set. So in other words, for the SQL statements we've found, we can then go back in time and look at the different execution plans that specific SQL statement has had. We can then, in the background again, test execute the alternative execution plans. So in other words, we can compare one plan against another at its simplest level. We can compare the performance results that we get, and then if a SQL performance regression is confirmed and a previous plan is better, we can create a SQL plan baseline for that previous plan. For those of you who like a picture, this is what it looks like. We can introspect. So in fact, it's the SQL Plan Management Evolve Advisor, which you're familiar with, I'm sure, goes looking in the repositories. We then look for previous execution plans in the automatic SQL tuning set and find out whether that SQL statement, find out the history, if you like, of that SQL statement, see what it's been doing over time. We can then add those plans to the SQL plan history, so that's a component of SPM, and then we can run the Evolve Advisor to test, execute, and check the performance of all the different SQL plan candidates, if you like, and see which ones are actually better. So the plans that are proven better and are shown to be better during this test execution phase, we can create SQL plan baselines for those plans. So in other words, we create a set of constrained plans for the SQL statements that have regressed. And then essentially we start the loop all over again. It's a continuous process. And so, of course, we're going to monitor what we've done, and we go around the loop, around and around again and again. So it is a continuous process, not something that just happens once. It's a periodic loop, if you like. So what does it look like in Autonomous Database? So if you're using Autonomous Database, what does this physically look like? Well, the truth is there's not much to see. You don't need to do anything. And also it's difficult to know what to see. I mean, you've got a query that is not working as well as it should, and then it works well again. Well, I'm going to just take you through what you can see. But of course, I want to emphasize that you don't need to look at this stuff. You know, I'm showing it to you for the sake of you being able to understand what's happening. But of course, in reality, being autonomous, there's no requirement for you to start looking at these things. You should just reap the benefits of them. So let's have a quick look at a demo. So in fact, I've marked this video with a bit of text. So if we run this query, it's just a fact and dimension join, pretty straightforward. One thing to note, it's not obvious from the queries, there's a lot of skew. So this particular region has got just a count of 1. So consider the case where you've got regions of different sizes in the database, and they can often cause data skew. So for some values, for some regions, there's lots of records from other regions and not a lot of records. So in fact, what's happened here is that, if I just stop it for a minute, we're using an index, and that's good because in fact the region 5 has just got a single row in this case. We've got a nested loop join. Notice actually there is a result cache that's used by Autonomous. So this is running in Autonomous data warehousing. So that's a little side thing that's going on as well. But it's not really important for the sake of this demonstration because we work around the fact that the result cache is there. So this is running on ADW, as I say. So we're going to set, in fact, what I'm going to do here is set the result cache to manual because I want you to see performance difference, because the result cache will just make everything run the same speed. So I'm just going to turn it off for now. So now we've got if you like, a query that's running. We can now see the IO that it generates. So that's why I'm turning result cache off. So there's a lot of manipulation going on through here that you don't need to do, but I want to show you so you can see it happening. So you got consistent get, so it's a fast query, which means we're only reading 6 blocks. It's all because it's all through an index, so it's nice and quick. Okay, so basically we've got a query that runs really well. So today everything's great. Different region. So now we're reading region 1. So this is a different query. It uses a full table scan this time, and it does that because there are now a lot of rows in that region. So I've got essentially a new plan in this case. You can see I'm reading a lot more disks. So different regions require a different execution plan, and that's very common, you know, when there's skew. Okay, so the thing is that in order to know that, the optimizer needs histograms. It needs to know that the data skew exists. So I'm going to do something nasty here. I'm going to delete the histogram, basically. Regather stats first, and then I'm going to kill the histogram. So let's do that. So what I'm doing here is now, so you'll see here, delete column stats. This is the key thing. So what I'm doing actually is something that could conceivably happen in a database where something has changed. A key statistic has been dropped. So now the optimizer is actually blind to changes in skew. It can't see it anymore. So to cut a long story short, I'm attempting to hurt my query. So it's a nice way, actually. I'd use non-invalidate equals false to basically get the cursor kicked out of the cursor cache, and I'm going to run the query again. 1 row, but now it doesn't know about the skew. So this is the demo beginning, really. So what we have, just to summarize, is a query that's accessing a skewed data set. And so it's very important the plan needs to choose between scanning a table or looking at an index, and that needs to change. I've killed the histogram, so the optimizer now has lost its way of knowing that there is skew associated with this region. So now it's just falling back on a plan. and the plan is a full scan, when really for region 5 we should be using the index. So remember, with the index we only read 6 blocks from the database. If we scan the table, we're going to read something like 100,000, I think it was, something like that. So this is the beginning of the demo. So this is the problem has now occurred. So what we have now is a query that is scanning the table. It's reading 111,000 consistent gets. So in other words, it's reading a lot of data now just to return a single row. So by dropping the histogram, we've hurt our query. So this is what's happened now. The user experience is, I'm just running my query and now it's gone wrong. So what can we do about that? So what we do essentially, like we can see, we're taking a look. Now what we're going to do now is wait. So time passes at this point. So remember, there is a cycle that we're moving around, and this is happening in the background. It's not something we're actively doing or actually setting up or changing or what have you. It's just happening. So if you try this on ADW, this is what's going to happen. And then it's typical, we have to wait, but I've shortened I've shortened it a little bit. It's not quite as quick as this, but now when I run the query again, I'm now using the index. So that's the user experience. It runs well, it runs badly, and now it runs well again. I've got the result cache plan again. So now the problem's solved. It's using the SQL Plan baseline plan, which is what I want. So everything is done. So that's really it. We can look around. We can run our query actually. So I run it now and take a look. What's the performance like now? Okay, none, because we're using the result cache. So there's no. So that doesn't really tell me very much. So I'm just going to get rid of the result cache at this point. I think that's what I do. Yeah. So I'm actually shooting the result cache because I've made a change to the table. I run the query again. Okay, and now we have our index range plan. We decache again. Then we run it again, and then, okay, we're back to 6 consistent gets, which is what we want. So we went through a phase of fast, slow, repair, fast again. So that's the key thing. And again, how the result cache is kicked in, we don't see any more IO. So that's how the result cache works for us. So you've got basically multiple things happening in ADW to give you the best possible performance. So we do have things like result cache in the background and what have you. But so that's what it looks like. I think we're going to take a look at AWR. So AWR has our SQL statement in it. So it relies on these things happening in the background. So they're being captured. So AWR has seen our SQL statement. So that's important. And then if we look at, so if we look at the plans actually in AWR, so these are the AWR plans, you can see also we have things like the full scan of the table. So we have that plan. We have the index range plan, scan plan as well. So we have about multiple different plans that we've seen over time and have actually been captured in AWR. We can do the same actually for the SQL Tuning Set. So this is the SQL Tuning Set. Remember, we have a system tuning set called sys auto sts. Again, we have this information. Now, the SQL Tuning Set is different from AWR because it's capturing everything we see, whereas AWR sees the more significant SQL statements, the one that consume the most resource. So there is a difference between the two repositories. But again, you can see that we have a whole set of different plans again captured. So all of this is happening in the background, okay? And then the bottom line is that if we look at DBA SQL Plan baselines, we have our SQL statement with an accepted SQL Plan baseline. So we know that, so this is the entity that is ultimately controlling our execution plan. Okay, so let's move on. So let's look at how you can make use of the changes we've made to SPM in an on-premises database. Now, the key point here is that this is something that you can use immediately, for example, if you are upgrading from 12C to 19C. It relies on you having AWR, and if you want to be able to do this on day one, it's useful also to have the SQL tuning set created with your workload if possible. So AWR, if nothing else, and also a SQL tuning set of your workload SQL over time, that's very useful as well. If you can do that in advance, then you're able to use this manual approach on day one. You can use it immediately to fix SQL performance regressions. So if you've just commissioned the upgraded application, you are in a position now to be able to resolve some of these performance issues very quickly. The key thing here is that you do need to know which SQL statement has regressed. So that part, if you like, is not automated if you're using an on-premises, say an on-premises 19C database, if you're using Enterprise Edition. So you know which SQL statement you want to repair, and then you direct this API. So you use this set evolve task parameter to say, I want you to look for alternative plans for my SQL statement in these sources. So we've got Cursor Cache, AWR, SQL Tuning Set. And in fact, you can use it at the end. You can say, figure out which of the plans you can find are best and then implement it immediately. So that's the kind of thing you can do. So it's a pretty short workflow. It's not an extended or difficult one, but the key thing you do need to do in this sort of streamlined manual approach is identify the SQL statement first. This can be any SQL tuning set as well. It doesn't have to be the system tuning set. So in other words, what you're saying here is, I want you to, for my SQL statement, I want you to go and look for alternative execution plans and figure out which ones are the best. We can look at that, in fact. I'm going to give you a link to this as well. So obviously you don't need to memorize all of this. There is a link I'm going to give you later on where you can try this for yourself. So I'm just going through the same process, really, running my query. It's looking good. Yeah, so I'm going to skip this a little bit. We're going to go through. We're actually going to kill the histogram, run the query again, and now we are seeing a full table scan. So there's me killing the index. So that's how you hurt yourself. So that hides skew from the query. So now it's going to default back to this full scan because it doesn't know any better. It doesn't know the skew exists. So now when I run the query, you can see I'm just reading a similar amount, actually about 100,000 consistent gets. So our query has gone from reading 6 blocks to over 100,000. So it's not going well at this point. Yeah, so I'm looking actually in AWR here, and I can see that I have some plans for that execution, for that SQL statement, I should say. So I can see the good plan I used to have. I can see the plan I've got now. So again, bear in mind that some time has passed, okay, because this has got to get its way into AWR first. Also, it's in the SQL tuning set, so I can see my SQL statement in there as well. So I can see the plan. There's a plan in there, and I haven't got any SQL plan baselines at the moment because I haven't done anything yet. I haven't initiated the fix, if you like. So let's skip ahead a little bit. So this looks fairly complicated, but it's not really. I'm just setting up an evolve task, which is something that you've probably done already. I'm just setting up an evolve task and telling it to look for alternative plans in these sources, as I showed you in the slide deck. So it's really a set. I call this kind of handle turning. So this little package just says, this is a SQL ID I'm worried about. Go and figure out how to fix it. That's really it. I'm actually towards the end. I'm using implement evolve task as well, which says, whatever you find, just implement it immediately. So it doesn't require any kind of further action from me. And at the end, I'm just going to get myself a report as well to see what actually happened. So it's, as I say, I call this a kind of handle turning approach. Of course, on autonomous, you don't do any of this at all. It just happens in the background automatically. But as I say, this is something you can do. So I'm going to run that repair script. And the way I'm going to do it is I'm just going to enter the plan that I want to fix for the SQL statement I want to fix, and then I let it run. So this is real time. Because it's a quick running SQL statement, it kind of happens straight away. It's pretty fast. So it's had a look and it can see that I should accept it. So it's telling me that the index-driven plan is better for this SQL statement. It passed the performance criteria for an improvement, and it recommends that I create the SQL Plan baseline. But because I ran the implementation step, it's there. So already now I have my SQL Plan baseline. Okay, so what have I done? I've told it, this is the SQL ID I want to fix. This is the plan I consider bad. Go and figure out whether there's a better one available to you. So as I'm saying, when you're thinking of upgrading, think about the ability to do this in 19C onwards, where you can, if you have the SQL Tuning Set, you have AWR, from your previous workload, from your previous pre-upgraded database, you're in a position then to use this feature for on-premises as well. Okay, so bear that in mind. It could be, you know, it's a really nice trick, if you like. It's pretty cool. So where to go for the details of this? So I've added, there's links in the slide deck you can follow. Generally, the source where I start, my starting point, if you like, is the Optimizer blog, so you can go there. But there's an explanation, a more detailed explanation of the Auto SQL Tuning Set, a post about automatic SPM, and that gives you logs there, links, I should say, into the GitHub repository, so you'll be able to see examples in there that you can try yourself. And that's it, really. Optimizer blog, starting point, autonomous database, of course, and the documentation, of course, always a good place to go. So that just remains to say thank you. Hope you enjoyed that. Hope you found that interesting, and goodbye. Thank you.